Hi everyone. I want to talk a little bit about insulators and conductors. And those are just like what they sound. An insulator is something that blocks the flow of charge. A conductor is something that allows the flow of charge to flow freely. A good example of a conductor is a metal, copper, silver, gold are all great conductors. An insulator, glass, rubber, anything that you'd use to protect an electric circuit is going to be an insulator. One interesting thing about conductors is that by their very nature, if there's any kind of charge that's on a conductor, any kind of static charge, that charge will only sit on the surface of the conductor. That's really because every piece of that charge wants to get away from all of its neighbors, because like charges repel. And the farthest away that these charges can get by sitting, when they're on a conductor, is on the surface. And actually, this is one of the ways that the early investigators of the electric force were able to transport static charge. Basically, you take something that's already charged, touch it to a conductor, because these charges, there's kind of a tension. They want to get away from each other. That charge will then flow into the other and basically separate as evenly as they can. And now you've got charge, you've got some left here, and then you've got some on the new place. There's another trickier way to do this. It's called induction. Basically, you take the same scenario where you've got a neutral conductor, you've got a charged conductor, you bring it very close without touching. Maybe even separated with an insulator to protect the flow. So no charge actually flows. But what happens in the neutral conductor is that a charge separation occurs. Those charges that are opposite are attracted. Those charges that are like are repelled. And basically you get this kind of motion inside the neutral conductor. Now what you do is you connect it to ground, just run a simple wire and allow the repelled charges to just drain away. You cut the ground wire, and now you've got something that's charged of an opposite polarity from the original. So not only have you induced charge here, but you still have the same charge you had before, and so but they're of opposite polarity. And so there's all sorts of tricks, and people came up with very complex and Rube Goldberg-like different ways of playing around with the electric charges. And that's how people kind of started out investigating stuff in the 17th and early 18th centuries. One particularly important combination is here, a capacitor. A capacitor is basically two parallel plates of conductive material separated by an insulator. And as the picture here represents, basically if you have positive charge on one side and negative charge on the other, those two plates, the charge on the two plates, will be attracted to one another. But because of the insulating material in between, they can't actually get to one another. So they're trapped, they're locked in place. And so a capacitor is a perfect way to store electric charge. And as the picture also represents, because of these opposite polarity, there's going to be an electric field inside the capacitor. The electric field is given by this very simple formula here. The epsilon naught, epsilon zero in the denominator showed itself in one of the forms of Coulomb's law originally. The numerator, that sigma there, represents the charge, the amount of charge per square meter on each of these plates. For mathematical simplicity, you have to assume the plates are infinitely large. That means you have a constant electric field. A real capacitor, of course, is going to have edge effects and different things that will make it deviate from this kind of mathematical ideal capacitor. But nonetheless, we can use this in our problems. Now, because of the connection between the electric force, the electric field, and potential, this is the formula for the potential, the electric potential that is trapped inside of a capacitor. And what we do is we represent its capacitance, basically the strength, the power. How good is this contraption at holding electric charge. We define it here by the ratio of the total amount of charge divided by the voltage that's required to maintain that. And this is the formula here for it. And basically it's a formula that's just basically in terms of the basic geometry of that capacitor. You know, the larger the area, the smaller the gap between those two make the capacitor even better. And that's that.